All right, guys, I know that first example and explanation and everything took a long time. It did. So let's look at example 2. This one won't take as long. We've learned what to do. We're just putting it into practice now. So we're not sketching this graph. We're just finding all the parts. So the very first thing we need to do is factor, factor, factor. If we look at the numerator, we need numbers that multiply to be 9 and add up to be 6. That's going to be 3 and 3. So this is x plus 3 times x plus 3. And that's going to be over that denominator. We have a greatest common factor, so we'll factor it out first. We'll factor that x out, and that gives us x squared minus 4. Now, we need to look very carefully at this because x squared minus 4 is a difference of squares. X squared is a perfect square, and 4 is a perfect square. So this will factor again using x and 2. So the x that's in front stays, and we have x plus 2 times x minus 2, the x and 2 coming from the square roots of those terms. Then on top, we have x plus 3 times itself. That is a squared factor. And so this is our simplified factored form. Nothing else here divides out. It's all good. Now, let's look at each individual piece here. Let's look at these wholes. There was no factor that divided out, so there is not a whole, just say none. If we look at roots, we set that numerator equal to 0. So that is x plus 3 all squared equaling 0. So x plus 3 is 0. So x equals negative 3. So our root is a point on the graph, would be negative 3 comma 0. And it's asking you about the multiplicity. Remember, the multiplicity is that power. Anything that happens with a squared power. So this is a double root. So this will be a tangent root on the graph. Vertical asymptotes happen when the denominator gets set equal to 0, and those we will have vertical asymptotes here. We have 3 different factors in the denominator. We have x equal to 0. There's a vertical asymptote. X plus 2 equals 0. So x equals negative 2 is a vertical asymptote. X minus 2 equaling 0. So x equaling positive 2 is a vertical asymptote. All 3 of those vertical asymptotes, and they are all singles. So writing really small, x equals 0, x equals negative 2, and x equals positive 2 are all vertical asymptotes. Now, for tangent together, we do have multiplicity of 2 in the numerator on top, that x plus 3 all squared factor. So we do have a tangent, it's on top. We have a tangent root at negative 3, 0. Then let's look at that end behavior. And that end behavior, we look at the degrees. The degree on top is 2. The degree on bottom is also 2. So those are the same. When degrees are the same, I lied. My mistake. I'm sorry. Degree in the denominator is 3. We're looking at the highest power. 2, 3. So in this case, the degree on top is lower. The degree on the bottom is higher. So low over high 0 equals y is the line in our poem. So that means there's a horizontal asymptote at y equals 0. So HA at y equals 0. And then the y-intercept is a point on the graph. Always use x equals 0 for a y-intercept and use the original form. So when x is 0, everything on top except the 9 divides out. And in the denominator, we have 0 minus 0. So that y-intercept is undefined. There is not, time out. That y-intercept is undefined. There is not a y-intercept here. And if we look at what's going on at that y-axis, we have a vertical asymptote at x equals 0. That is the y-axis. There is a vertical asymptote on the y-axis, so there is no y-intercept. Now, let's go on to example 3. Now, we want to factor this. If we look at x squared minus 25, no greatest common factor. That is 2 terms. So we look for squares or cubes. This one happens to be squares. So x and 5, each squared. So that top factors as x plus 5 times x minus 5. Then in the denominator, we have a greatest common factor that is x squared. So we divide out the x squared. And when we divide both terms by x squared, we get x plus 5. Now, that is completely factored. We notice we have a common factor, top and bottom, x plus 5. That will divide out, and that will leave us with x minus 5 over x squared. And this is completely factored form. Now, because we had a factor divide out, we really do have a hole. Pink. Anyway, we really do have a hole. So to find the value of the hole, we take that factor that divided out, x plus 5, set it equal to 0. So its x value is negative 5. To find its y value, we plug into the simplified factored form. So negative 5 minus 5 on top and negative 5 comma or parentheses squared on bottom. That is negative 10 over positive 25. Divide all that by 5. We get negative 2 over 5. So negative 5, negative 2 over 5 is a whole. Negative 1, 2, 3, 4, 5. Just a little bit below the axis. We don't need to be super precise there, but we need to be close. Okay. Then to find the roots, roots are on the x-axis. So roots happen when the numerator is set equal to 0. So x minus 5 equals 0. X is 5. The root is a point. It's 5 comma 0. So 1, 2, 3, 4, 5 is a root on this graph. Then take a look at vertical asymptotes. Vertical asymptotes happen when the denominator is equal to 0. So x squared set equal to 0. That means x equals 0 is a vertical asymptote. So, I don't want a lighter color here. This y-axis is a vertical asymptote. That y-axis is a vertical asymptote. Let's make that to show up. So our graph will approach but not cross that y-axis. In the tangent or together, we're looking for squared factors. We do have a squared factor in the bottom So tangent together's on the bottom. We do have a together at that vertical asymptote of x equals 0. So at that vertical asymptote, the graph will approach the same direction. If we look at end behavior, we have a degree of 2 on top. We have a degree of 3 on the bottom. That's a low over high. 0 equals y is our piece of poetry. So that end behavior means we have a horizontal asymptote at y equaling 0. Well, y equals 0 is the x-axis. And if we look at this in terms of an asymptote, we see that our graph is crossing that asymptote. And the deal with horizontal asymptotes only is that the graph can cross it in the middle piece of the graph, but not on the far ends. That is end behavior, so on the far ends of the graph, it will approach 0, but not touch 0 on the far ends. So looking at the y-intercept, of that graph is always when x is 0. So y is, I would use the original unfactored form. Okay, anything with an x becomes 0. So that top is negative 25 over everything in the denominator has an x. So that y is undefined, meaning there's no y-intercept. And if we look at the y-intercept, we already know we have a vertical asymptote on the y-axis. So this is enough to sketch this graph, okay? And here's how. We know from the whole to the left, the graph has to follow the end behavior. So from the whole to the left, we're approaching that horizontal asymptote but not crossing it, because there's no other key features to the left of this. So from the whole to the left is the end behavior. So as we go to the right, that graph has to approach that vertical asymptote. It has to go down. Towards that vertical asymptote, keeping that piece of the graph within those asymptotes. Now, the other piece. This is where the together comes in. Okay, we have a together at that asymptote at x equals 0. So what that means is that both sides of x equals 0 point the same direction. And in this case, they are both going to go down. So we're going down to make the together on that graph. Okay? Now, as we're going up, we have to go through this root. We cannot cross the x-axis at any other place. That's why this hole could not cross from the hole. We could not go up. That's why we could not go up here. We don't have an x-intercept to cross. Okay? So we do cross the axis, cross through that root, and the end behavior is still that horizontal asymptote here. So we cross it and then approach it here. So it does go just a little bit above that axis. And there's our graph. Can only cross the x-axis at the roots we found, cannot cross any other place. So this domain, any domain, breaks at holes and vertical asymptotes. We have a hole at x equaling -5. So from -infinity to -5. Then we start over again at -5, and we go to the vertical asymptote at 0. And then we start again at 0 and go to infinity. So there is our domain. Now, in example 3, we want to find some of these limits. So let's look at our graph and let's look at what's going on here. A and B are asking you for the limits as x is approaching -5. There is a hole. We have a hole at x equals -5. So if we look on the graph at x equals -5 and we look at its left and its right, that y value is approaching the y value of the hole. The y's approach the y value of the hole, but because it's a hole, we don't actually touch it. So the y value of that hole was -2/5. So the limit on either side of that hole is -2/5. So at a hole, the y will approach the y value of the hole. Let's probably call this f of x. At the hole, f of x approaches the y value of the hole. Now, let's talk about the limit as x approaches 0 from the left and the right. X equals 0 is a vertical asymptote. So we are looking at what is going on the left side and the right side of this vertical asymptote. Both sides here are going down. They're going the same way because of the together. Left and right are going down. So both of these sides of the asymptote, the left side of the asymptote goes down, the right side of the asymptote goes down. So in general, at a vertical asymptote, the f of x will approach either positive or negative infinity. At a vertical asymptote, we will approach positive or negative infinity. And let's look at these last limits. We're looking at the limit as x approaches negative infinity. That is the far left edge of the graph. As x is approaching positive infinity, that is the far right edge of the graph. So if we look at what the far left and right are doing, on the far left, that graph is approaching that horizontal asymptote at 0. On the far right, that graph is approaching the horizontal asymptote at y equals 0. So both of these limits here are 0 because that is what our end behavior is doing. So in general, as x approaches either positive or negative infinity, the f of x is approaching whatever the end behavior is, whether it be a horizontal asymptote at 0 at some other number or a slant asymptote. It approaches wherever the end behavior falls. All right, y'all, that's graphing rationals. It's a lot of pieces. It's a lot of little things. Do each little part on its own and